Thank you
Hello
for
and welcome to our interview series for physics at Mount San Jacinto College. Today I'm going to be with Mr. William Baker. If you would, could you introduce yourself and talk a little bit about your physics background?
sure. So I am William Baker. I currently teach at a public high school here in Maryland. And before that, though, I went to a university here called University of Towson, and that is where I got my physics bachelor's degree. And then I went and tried to get my PhD at the University of California, Riverside, but decided that the entire process wasn't 100% for me. Kind of just the was more in line with learning about the physics. I think the research aspect was just not exactly what I was looking for. So I transitioned to becoming a teacher since when I was a graduate student, we did have to teach undergraduate students, and I found that fulfilling, interesting, and fun.
All right, great. I'm going to start out with some questions that are going to be a little bit different for you because you're not currently doing research and you have a more broad background than the other ones. But generally, I'm going to ask everyone I'm interviewing more or less the same questions and then go into more specific questions based on your background. And the first one is, what drew you to physics against other areas of study? Why did you choose to specialize in high energy after doing research in astronomy?
So the reason I went to physics is in high school, I remember we had a physics teacher that really kind of made it fun, made it interesting. And I always liked the idea of like we were learning how the world was like operating, not just like, the things we see on the surface level, but like why, electrical components work this way. Why like do things fall or interact this way, like crashes, momentum, acceleration, all of that stuff. That was really interesting. And then as I was going through my undergraduate career, I kind of liked like talking about energy in like my physics 2 and physics 3 classes when we learned a little bit more about energy and electrical systems and energy in like a little bit more of a quantum way. Quantum mechanics was fun for me. I know not a lot of people say that, but I thought it was interesting fun because like you learned more in depth again, that idea of like how things work, why things happen the way they do. Um, and though I did do astronomy research in undergrad, it was high energy astronomy research. I was
Yeah.
looking at black holes and looking at intermediate mass black holes, and I was doing an internship where I looked at the gamma ray binary star system. So all that was kind of like what I was really looking at were natural particle accelerators, more or less. Like I was looking at the particle accelerators that nature provides us, and we can look at and see what's happening. So that's kind of like it was an easy transition. Like I wasn't doing significantly different work. It was just what tool I was using changed from a natural process to one we were creating.
Okay. Nice. And what does physics mean to you in general? Since you teach general science as well as specific science, what are the boundaries that you put up when you're teaching physics versus other types of science? And how does physics, as you've learned it, impact the way that you think about your experience and the world around you that aren't necessarily immediately obvious?
So I don't know if I put any boundaries up between the way I teach like a general science and a physics class. I guess with my understanding of physics, it's kind of looking into how things work, how things operate, kind of asking questions, and that to me just sounds like the scientific thinking about, okay, why does this process lead to this and then that? And I teach a Earth systems class where we go over things like climate change and habitat interference and stuff. And like we learned recently about keystone species. And to me, that was like a really instructive lesson for students because we were like, okay, why did reintroducing the wolves to Yellowstone Park lead to the rivers in Yellowstone Park becoming more stable and less erosion? And it's this process of, okay, they had the deer move, which then caused the vegetation to grow, which then caused the root systems to become more stronger and solidified, which then held on to the dirt and soil along the riverbanks, which then cause less erosion, which then cause calmer rivers. So it's that kind of like looking at point A, point B, and seeing everything in between. That kind of inquiry process and learning about that is uh, how I try to do both and approach that. And it's kind of like why I like physics, why how I think of physics in the everyday is thinking about different aspects interplay with everyone or everything. I know in one of my classes in undergrad, a professor told me or was talking to the class about how one day they were on vacation and they were at the beach and they're just like, how do waves work? And they were just thinking through their head all the processes of like, okay, so I know the moon, but like, what is it? Is it gravity? Is it something else? And he went through that, and I remember thinking that will never be me. That sounds like you're no, you're going too hard. But like, I found myself sometimes thinking, like, how does that work? And then like thinking it through, going through, just kind of like always asking, how does this work? How does that function?
Okay. Yeah. That's something that I also ended up having when I first when I first started physics in undergrad. I had taken a high school physics class, and the first year of physics was pretty condensed for me, so I didn't have as much of a chance to think about things. But once I started taking classes at a more leisurely rate, at a more sustainable rate, I would just go to amusement parks or the Santa Cruz Beach Boardwalk and think about like how conservation of energy was at play with the or momentum or all these mechanical processes were at play, and like how to actually derive the equations that we more generally just kind of take for granted at a certain level, I think.
No, yeah, like I know, like I play golf as like a hobby and everything. And like, let me tell you, I'm thinking about classical mechanics all the time when I'm like, okay, like I need to hit this ball lower, so let's lower the angle. Put my club forward to lower the angle so it has a lower launch angle. To shape the shots, you have to hit it different ways to impart spin, so it spins that way or the other way. So it's kind of like I'm always thinking about that as I'm playing.
Yeah. And then I'm just going to be very Southern Californian and say that it always comes up when I'm driving because I'm Southern California, so I'm driving 3 hours a day.
Mm.
Yeah. But yeah, can you describe the research that you have done, the how and why of it, meaning how you did the research and what motivated you to, or what motivations led to you just designing experiments, even if you were an intern for NASA, it might not be you specifically designing experiments, but how generally people would design experiments to find specific
Information out.
physical ideals and physical parameters that they were looking for.
Yeah, so I've done three main areas of research. I've looked at intermediate mass black holes. I've looked at the gamma ray binary star systems, and then in grad school, I was looking at the interactions gluon plays or play within the intrinsic spin of particles. So to start with like the intermediate mass black holes, that one is there are sources that are bright enough to be much brighter than stellar mass black holes. And stellar mass black holes are just black holes that form after a giant star collapses it and goes supernova. If they're big enough, they have a core collapse where, all the mass is condensed into one point. You break some like the Pauli exclusion principle and everything, and then you have a black hole. But usually those are a few solar masses, and solar mass is just the mass of the sun. So we're like on the order of five solar masses, and they're bright, but they're not super bright because of all the material around them. It spins around, heats up as it gets closer and closer due to friction. And this kind of disk of material spinning around the black hole is called an accretion disk, and that is what we can see of a black hole. So, like, we don't see the black hole, we're seeing the stuff around it. But because of the size, it has a certain angular momentum, so a certain friction, and then so a certain brightness. And then we have supermassive black holes, like the one in the center of our galaxy and in most galaxies, that are much, much brighter than stellar mass black holes. But we were finding these objects that are kind of like in between, intermediate between them. And if we were to use the equations that we were looking at for normal stellar mass black hole accretion disks, the masses of these objects would have to be on the order of hundreds of solar masses. So not quite the thousands upon millions of solar masses a supermassive black hole is, but definitely much larger than a stellar one. And because of the location where they're at, some of these sources are very isolated. So it isn't the idea that they were just smaller black holes that merged together is harder to assume with all of these sources. So a lot of my research was looking at luminosity data, looking at all of this for different black holes, definitely these intermediate mass black holes, and coming up with different accretion disk geometry. So what I mean by that is how is the information fall, how is the all these particles falling into the black hole? Is there a way where we can say it is a stellar mass black hole, but with a different accretion disk, a different way that was creating this light to where we could have a higher luminosity while keeping the overall mass in a spot that we know. And so far with like the research I did and the research a bunch of other people did who um, know this a little bit better than me, it does not seem like you can really get a geometry that would give you the luminosities, the brightness that we see with normal stellar mass black holes. So the research now, as far as I know, is moving away from trying to figure out how a stellar mass black hole can create this light to how can we get these intermediate mass black holes, these 100 solar masses to 1,000 solar mass black holes. Then when I was interning at NASA, I was looking at gamma ray binary star systems. And all that is more or less you have two stars. One has already kind of lived through most of its life, so now it is a small kind of white dwarf, and it is rotating very quickly, while another one is probably around has grown exponentially, but is releasing a lot of particles. And as the second star is orbiting the first one, it is going through this giant cloud of gas with its own emission. So it's boosting its X-rays emissions into gamma rays as they kind of have Compton effects and all of that going on. And we're able to get a very good time signature as it happens, periodically, and it's not really changing too much of what's happening. But we're also able to get a really good data set and information about the environment that those stars are in. And that I was using data from uh, NuSTAR, which is an X-ray telescope, kind of like Hubble, but it's looking at a different frequency range, a different kind of wavelength compared to visible light and infrared like Hubble does. And using that, we were trying to get the environment of this system and kind of understand what was going on there. And then at Brookhaven National Lab, when I was in grad school, I was looking at particle collisions of protons and that to see how the gluons within a particle, so the things that kind of hold the different quarks, which make up the different particles of protons and neutrons, how they impart and impact the spin characteristics of these particles. And the way the experiment was set up there was we have a particle accelerator, which is usually built in a circle. And the reason it's built in a circle is because since it is a loop, we can continually loop the particles around to build up speed. And we did that by using magnets and electricity to bend the particles around the pipe as they were going through. And as we did that, they built up speed and speed until they got to almost the speed of light. And this allows us to hit these energies that allow us to break these particles apart and look at the gluons, look at the quarks, look at the pions, and all of these different particles within. And due to the way we have the detector built, where you have a bunch of, it's pretty much cylindrical, you can get and all this information after they burst. So they hit, they go out. But because we can track where everything hit and went away, we can make a kind of backtrack map of where the interaction occurred. We can use that to kind of figure out, okay, what was the energies of things in, energies out, what particles were created, and then using our understanding of particle physics and high energy physics, we can kind of understand what was created, what was made, what was kind of the processes that happened after that collision.
Okay, nice. So now that we've gotten a bit of background about you, I'm going to move on to specific questions that students who are in the class want to ask. The first one is and I quote, I would like to ask physicists what motivates them to get into a career and what jobs can you get by being physicists? And if it's hard to get into a program, I believe is competitive and what helps to be proficient in this major and what it takes to achieve this, especially astronomers. Do you want to work for NASA? What do you want expect as an outcome? And also, I would ask them about planet Mars and if it's true that people in the future will live there and what would happen to planet Earth. So, you did work at NASA in an internship, so I think that this especially is a good question to have for you because you did kind of get the dream internship for
It was
astronomers, and
really
then
fun. Um, the cool thing about the internship was also that like I guess because it's like a such a high place of learning and respect, they had a lot of cool talks happen there. So during that summer I was interning there, I was able to go to a lot of seminars and a lot of talks from different people in different fields that I had not knew nothing about, but it was just interesting to go to. And like the person who was I was interning under, like kind of, I think this is also a big part, told me to go to some of these talks. Like said, hey, you can take an hour out of the day to go to these talks because like you're here to learn. I don't want you to just be cooped up and, you know, typing away on your computer, doing the programming and all of that. I want you to learn. I want you to find something that, okay, maybe what we're doing exactly isn't what you want. In case I did like the research we were doing, but it was just like, you should see what's out there. You shouldn't pigeonhole yourself right away. So I think part of that, like the internship at NASA was definitely not just they had a lot of cool experiences, but the person who was interning me was definitely open-minded about the idea of like, you're here to learn, you're not here to just like do work for me, which I think is a good thing. In terms of kind of careers you can get, careers that are available, honestly, like if you do physics, you up a lot of doors because to do physics, you need to understand statistics. You need to understand data analysis. You probably will learn coding. You will understand math on a higher level than most people. You'll also understand engineering concepts. So like doing physics, you can be an engineer, you can be a mathematician, you can be data analysis, you can be a statistician. So like you can work, I know people who do work in finance, who work at the stock market. You can work in a bunch of different fields just because you get a bunch of different skills under you as you go through a program. And then for some of the other stuff in terms of how to look competitive, how to do all that, honestly, just do research and do research you like. Because if you don't like the research you're doing, you are going to not get as good a result. So, the research I was doing, I was able to go to some conferences in undergrad because I liked it. So I was like willing to push myself a little further than if it was research I didn't like. And because of that, I was able to go to the American Astronomical Association's conference when it was in Baltimore with some friends, and that helped me meet people. That also gave me some information and some stuff to put on my resume when I applied for that internship at NASA to kind of put me above other people who might not have completed research or they were just starting to try to do research. So honestly, if you're in undergrad, I would say do research as quick as possible, but make sure it's something you like. So if you find it out, oh, this research I don't like, switch and kind of shop around a little bit if you can to trying to do something you do like so you can be more invested in it, want to go further in it. And then that way you have more results to show people when you're trying to go into more of these competitive programs.
okay, yeah, that is very good advice. I agree on basically all points. You don't want to get stuck in re doing research you don't like, especially. Uh, I know a lot of grad students that just kind of started research in graduate school, and they you're allowed to choose your advisor in graduate school, but once you choose your advisor, it's very hard to
Yeah, switch.
switch. So it's good to get a good idea of what you want to do as soon as you want to do it. Or,
Yeah. And like it is okay if you don't know what you want to do right away. Like that is, I would say, one downside of graduate school is because you kind of are locked in, it does make it hard to switch if you are like, oh, I like this aspect of my research, but the current research I'm doing doesn't dive into it enough. You can't switch as easily or move around. So I would say definitely in undergrad, try to talk to some like different professors. Maybe, sophomore year, do research for one professor, junior year, do it for another, and a third for senior year. Or if you find what you like sophomore year, just continue doing that. Do more research with them to uh, build up your credentials in that field.
Okay. Yeah, very good advice. There was something about Mars, but I think there's another
Oh
question
yeah,
about Mars coming down.
the Mars and like if people would live there in Mars. So with that, I do think we will be able to go to Mars and be able to uh, look into it. But one problem with Mars is its mass is about 80% of Earth's, if I remember off the top of my head, or less. But more or less, because of that mass, Mars doesn't have an atmosphere because it is not massive enough to hold on to its atmosphere. And what I mean by that is the sun is creating a solar wind. So because of all the light, it flows out. That light has a momentum with it and will interact with the atmosphere of a planet, and it will push it away. Earth, luckily, has enough gravity to keep that atmosphere trapped on Earth for the most part. Um, Mars, though, does not, just like the moon and just like Mercury, they are too small to hold on to their atmosphere based off of how strong the solar winds are. While the planets we know that can keep it is Venus and Earth, which are about the same size. And because of that, I don't think from my understanding, terraforming it will really do much. Like if we live on Mars, it's not going to be like us terraforming it to look like Earth again. It's probably going to be kind of more subterranean. We build into the rock because the rocks can provide natural shielding from the radiation of the sun. And then we would use it as kind of like a second home potentially, and things like that. But I don't think we kind of like Carl Sagan, who's a old school astronomer. I don't think we can ever really leave Earth. Like this is our home. Like I don't think Mars is the solution to climate change. Like we should fix climate change here on Earth other than going away to Mars. And that Earth will still be here even if we go to Mars. And the only reason, if you want a cool fact, that we would need Mars to survive as a species is when our own sun undergoes a helium flash in about 4 billion years, it will expand to the size where Earth will then be in the sun. So Mars will not, but Earth will be. So that would be the only time we really cannot be on Earth at the same time as Mars. Um, so that's what I would kind of say about that is like Mars is definitely a place we can kind of go to and live on. It just, I don't think would be the way that some sci-fi kind of books and movies have shown it, where like we terraform it to look like Earth, just because I don't think it can hold on to the atmosphere.
Okay. Yeah. And then I think also this is a bit of a tangent, but I think that when we were talking about life on Mars initially in the late 1800s, a lot of the ideals did actually just by coincidence be about instead of terraforming, they were doing large engineering projects. The Martians were supposed to be doing large engineering projects and living underground, which is why we couldn't see any cities. So I find it interesting that that does actually kind of become a possibility for when we would actually move on Mars. And another tangent is that I think there is a popular science book out recently by cartoonists that I like, uh, which is called A City on Mars, which is about all of the different problems that you would have actually being able to terraform Mars if you want a really, really in-depth look at it. It is by Kelly and Zach Weinersmith. So I just want to plug that, even though I
I would
have
say
no
one,
connection whatsoever. I just think that it's a good resource.
I would say one problem with living on Mars isn't necessarily living on Mars, but because Mars has such lower gravity than Earth, when you go back, you probably might not be able to go back to Earth for long periods of time because like Earth's gravity would be much heavier. So like your bone structures, if you were born and lived on Mars for most of your life, your bones would be less dense and wouldn't be able to handle the gravity of Earth. Like that's one reason we can go out to space and go to these less massive planets is less gravity doesn't hurt you, but more gravity can.
Yeah.
So like going from Mars to Earth could be a problem in the future where like no, that wouldn't be a process that could happen. I don't know exactly all the biology that would go into that in terms of like how long, like if it would like break bones or anything, but I just know it would probably be very painful for Martians to come to Earth just because of the gravity of the planet.
Yeah. Yeah. I think that's also something I can't remember what book, but that is something that came up in a sci-fi book that I read. So science fiction might not be completely scientifically accurate, but it does have some like interesting nuggets in there as
Yeah.
well. Yeah. Okay. And next question. What discovery or breakthrough in your field do you think has had the most unexpected impact on everyday technology?
I would say in my field, not. It would be hard for that in high energy physics and astronomy or for everyday technology, just because like a lot of it is very specialized and focused on quantum mechanics. Um, but if we go back, I would say just like the like with some of the first experiments is just understanding how charged particles work. Because like having that with like the bubble chambers and everything to see how we can apply electric field to move particles around and influence fields has definitely helped out with electronics and has helped out with communication and everything. I know one thing that is a big thing that hasn't done everyday life, but was happened about a decade ago now, a little bit more, is the Higgs boson being discovered in CERN. Has really revolutionized particle physics because it's allowed us to not just we know that now this theory is correct, and we can extrapolate from that other theories and other ways to help unify the different fields of physics, unify like our basic understanding of physics so we can build better models and kind of delve deeper into all of that.
Okay, yeah. And then one thing that I said about astronomy and uh high energy physics when I was talking about the beginnings of physics is that a lot of our ideas, like even the idea of what a force is in the first place, does come from like observing the stars and observing these fundamental
Yeah.
forces on a massive level or on very small levels.
Mhm.
Yeah. And then Uh, another quote. One question I have for high energy says particle physicists in regards to the semi-direct fermion, which is going to be very complicated for a conceptual physics class, but I want to ask it. I just want to see if they can better explain how a quasi-particle is predicted to have mass in one direction and be massless in the perpendicular direction, as it is hard to grasp the concept. I actually don't know anything about this. I know about quasi-particles because I used to work in condensed matter, and most of what you see is quasi-particles, which are not are mathematical objects instead of like an actual electron moving through a particle or an actual electron moving through a condensed matter space, so like a computer chip or something, you might have a hole, which is a lack of an electron, but behaves mathematically like a
And
particle.
electric, or yeah.
So I don't
Um,
know if you know anything about semi-direct fermions or not.
talked about it a little bit in grad school, and it wasn't my big research, but from my understanding, so like you do have in one orientation it's massless, and another orientation it has mass. It comes from a lot of like symmetry arguments. So like in particle physics, there's a lot of symmetry arguments. So like you have to have, conservation of energy, momentum, charge, parity, and parity is just kind of like time stuff. So a lot of that. So like from my understanding, the like it's all because when you look at it in a field perspective, and what I mean by field perspective is if you go to like quantum field theory and stuff, a particle isn't like a little like marble or a little point source or anything. You have like this giant fabric, this giant shield of field, and all a particle is a discrete perturbation or disturbance in that field. So like a neutron or a proton or an electron lives within what we call the Higgs field, and they are created when the Higgs field bunches up a little bit, and then you get a particle. And I think if I remember correctly, because of that field orientation and because of the ideas of reference frames and how, you're moving, that is how you get the massless part and the mass part. But we didn't cover it too much, and that wasn't really what my research was on, so I didn't look into it that much. So I'm sorry if
Okay.
that is not a sufficient answer.
Yeah, I think that's a very complicated question, and I don't think that anybody that we're going to be interviewing is going to be able to answer it because I think it's going to be you have to be doing research specifically on that to kind of be able to answer that, and I don't think anybody that we're interviewing is going to have
That
that
research experience.
specific experience. Yeah. But what are the biggest challenges when it comes to energy loss, like heat or radiation in extremely high energy levels you work at? Does it work the same way as when you with a particle? Does it look work the same way where you have friction taking energy or heat away as it does when you have more massive objects such as a car, let's say?
So like, for like high energy, like what is the energy loss within high energy? Um, Honestly, the energy loss in high energy physics is radiation. So radiation is not just like what you think of with like the Fallout games, nuclear materials. It is just like if you have an electron, which is a charged particle, if it moves at all, it releases light, more or less. And that light has energy in it, and that energy comes from the electron. So because of that, that is where you have energy loss within particle physics, is this movement of charge. So there isn't like a friction like we think of it, like if with your tires on the road, your shoe on the ground, there isn't that friction force or heat that is released necessarily, but is mostly out of radiation because we have these moving particles. So like at a particle accelerator, that is why we have these magnets to they ramp up in strength. So they start small so they can have the particles move slowly at first and they build up and build up and build up so they can keep this circle, but they can keep up the speed. Now, the energy loss there through the electrical component is definitely due to resistance within components. And we also want to make sure our magnets and all our stuff are working efficiently. So, and also to make sure they are superconductors to kind of help the electricity flow as smoothly as possible, we pump liquid nitrogen in because that's super cold and it keeps everything chilled, has things act as superconductors at those temperatures, and it keeps all the components cold so they don't overheat. So, like in terms of the experimental setup, there's this normal like resistance within the electrical components, but within energy, within like particles, they don't really feel a friction or a heat loss. It is because they move, they create light, which is radiation, which is energy leaving them. And the cool thing about that, though, is we can also use that to our advantages in astronomy. So with black holes and things that have like those accretion disks that are spinning, because they're spinning so quickly, they undergo something called synchrotron radiation, which is because they're moving, the light that they create becomes very focused as you get higher and higher energies. And then we see that and we can use that to understand how fast the object is rotating because of how like the pulses are. And that's kind of like the basis of a pulsar, which is a neutron star that kind of has these like two beams of light. And if they're in an orientation where we can see them kind of passing us like a lighthouse, we can kind of get the rotation of that pulsar. So we can use that loss of energy in useful ways as well.
Yeah. And then I'm also teaching an astronomy class at MSJC at the same time, so I just actually went over pulsars a couple days ago.
Yeah, they're fun.
Uh, and uh, from that, and from the ideal of pulsars, and uh, we were able to come up with also like different ideals or like proof of different types of stars and black holes that weren't necessarily believed before we had that theoretical evidence because there's a conservation of angular momentum, which means that the pulsars are spinning way too fast for anything to be bigger than what a neutron star is.
Yeah, because like a neutron
So
star is fun because like it's pretty much 1.5 times the mass of the sun condensed into a size like a sphere with the radius or no, the diameter of Manhattan. So if
yeah,
you look at Manhattan, you take like that whole length, that is, and then you just make a circle out of it. That is the size of a neutron star, but it has 1.5 times the mass of the sun.
yeah. And it's crazy that, as you said, because the radiation's coming out of it, like we are able to see objects that are about the size of Manhattan, uh, light years away from us, just because of that radiation and just because of how we are able to keep track of it here on Earth. So, going back into what you're saying, radiation is very useful tool for like learning physics and learning more about astronomy.
Yep.
So, um, do the laws of conservation of energy and momentum work the same way in cosmic processes as they do on Earth-based systems like hydrogen power?
Uh, From my understanding, yeah, because like those laws of conservation of energy and mass and momentum and all of that are like they are fundamental to everything. So like when we do our research in particle physics, like we keep, okay, the energy is this at the beginning, so it has to be this at the end. So if we see a particle after a collision that has less energy, we have to look, okay, what like if we had like 100 electron volts of energy and the particle we get at the end is like 70 electron volts, we know, okay, let's look for a particle that has 30 electron volts. That way it equals 100. And then when we find that particle that might give us new information, and that's actually how they kind of did it with the Higgs and stuff, is in a lot of things, they look for energy that should be there. So, and like they take the energy that we know of things we know, like pions, muons, and stuff, subtract that from the energy we put in, and now we know, okay, this is the energy we're looking for. And they use that energy to kind of look at all their data and kind of say, okay, where are we seeing spikes in our histograms? Oh, we're seeing it at this 30 electron volts that we're looking for. So that might be the candidate that we need.
Okay. Yeah. Uh, yeah, I think that there were physicists in the 20th century when we were first discovering quantum mechanics that were just trying to completely throw out
Mhm.
conservation of energy. I don't recall which uh, one it was, but it was one of the major physicists in the quantum mechanics. Every time he came across a problem, he would just say, "Well, this is a lot easier if we don't have conservation of
Conservation of
energy,
energy.
so let's just throw that out." But
I
it,
know. Oh, go ahead.
but I think, and I also saw a popular science video recently that said that conservation of energy can't occur in an expanding universe by like some complicated mathematical symmetry arguments.
Mhm.
And I think that these like this is a very useful term, or conservation of energy is very useful ideal, and uh, it's kind of easy to want to get rid of it because at high energies or high velocities or high gravitational fields or very small fields or something like that, it might become difficult to calculate, but the way that we have used it and we continue to use it, I think it does still hold up as a whole,
Yeah.
despite what you might see on YouTube videos.
I know one place where you can kind of get a little wonky with it is Hawking radiation.
Yeah.
So Hawking brought up the idea that um, you can create things from nothing if you have the antiparticle created with it. So if you have in the vacuum of space, and there is nothing stopping this, from nothingness, you can have an electron and an anti-electron, so positron, be created because they have uh, different masses. different charges. When you add them all together, they still create zero, right? Like one plus negative one gives you zero. And that's what he posits. But if this happens close to a black hole, such that before these particles recombine to create nothingness again, one of them gets sucked into the black hole, you have effectively increased or decreased the energy in the universe. Now he questions and posits, and people talk about, well, does a black hole, what happens in a black hole? We don't know. So they say, the reason this could happen is because maybe the black hole is keeping that energy within the universe. It's just within itself now instead of, you know what I mean? But that's kind of like a weird kind of thing to think about of like, you can kind of artificially increase or decrease it by this Hawking radiation.
Okay, yeah, that's interesting. Like that's an interesting way to understand it. Considering the way that I learned it is, it sounds like this might be more of a hypothesis than something that we know, for sure, especially because
Mhm.
black holes live on such large timescales that we're not able to really measure, uh, things, or we're able to see big changes in black holes as we look from one to another, or astronomical bodies in general as we look from one to
But we
another.
can't like looking at a black hole day to day is not going to give us a lot of useful information.
Yeah, but so the way that I learned it was that this change in energy was equal to E equals mc squared, where m is the mass of whatever particle escapes, and then the black hole is theorized to actually evaporate, and lose its mass and lose all of the energy that it has over the course of like astronomical timescales, due to losing that energy to Hawking radiation.
Mhm. Yeah, so like that is like the more like academic way of putting it.
Yeah. Okay. But as I said, I'm a condensed matter person, so
Mhm.
I'm just I'm not an expert in it. I know enough to understand and like be able to impart my wisdom on lucky students, but it is not what I did my research in, and you are probably going to have a better idea
Mhm.
of it than I do. So, uh, duh, 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 duh. uh, so, one question, and this might be helpful with a more general science background as well, is are there kind of theoretical parallels between anatomy cells and particles atoms? So the difference between atoms and cells, seeing as both are the building blocks of matter and the structure of life in general. So do you think that that is a useful way to look at the comparison between, say, physics and biology, saying atoms are the building blocks of physics and cells are more of the building blocks of life?
I could definitely see the comparison. I guess like the way where I think though is that it's like from my understanding, the reason we call like the nucleus of an atom a nucleus and the nucleus of a cell a nucleus is they kind of the cells were found first. So some of that stuff was done first, and then they, as scientists were understanding particles and understanding atoms, they were then kind of copying the cell nomenclature, the cells, the way we kind of named everything. But I guess the way I think of it is a cell is still made up of atoms. It's like it's made like a human cell, an animal cell has like carbon and all of that in it. DNA is made up of atoms. All of this stuff is made up of different particles. So like, um, I see that like, cells are made up of these different atoms, these different particles that then can make up life. Like it's definitely connected. I just don't think there is like outside of using some similar terminology, I don't think there's a ton of connect like you wouldn't glean a lot of good connections between thinking that a cell and an atom are similar just because like with a cell there's a defined wall to the cell, there's a defined outside, but with an atom there's no like definitive end to an atom. We definitely say there is just because like um at some point the electron will fly off, but like the electrons don't like orbit like we think. It's a cloud because it's the probability of where the electron is compared to the nucleus of the atom and all of that stuff. So like I think a lot of that like nucleus and talking and building block of stuff is used to kind of communicate the ideas that these things represent, but you can't glean a lot of really good useful information from like saying uh like they completely branch off. Like if I tried to talk about anatomy in terms of or in biology in terms of particle physics sense, I would pretty much just say we are all a bunch of discrete perturbations within a field.
Yeah.
And I don't think that has much use in biology from my understanding. Now, I could be wrong. I'm not a biologist. They might, tell me I'm very ignorant on this fact, and I will say, honestly, you're probably right.
Yeah. Yeah. Another thing to bring, like, with the idea that atoms make up cells, I just want to talk about very briefly, the etymology between the words, where atomus means unbreakable or like the smallest possible unit, because we thought that at the time that what we were finding was the smallest possible unit of knowledge, and a cell was
Yeah.
named after a cell which keeps inside of it a lot of different. It keeps inside of it a prisoner, but or a person who's living in a cell, and that's because a cell keeps inside of it a lot of different complicated life beyond just a nucleus and some electrons. So a cell is a much more complicated structure, even from its very basic definition.
Yes.
And then,
Computational power, we cannot model above a hydrogen atom. And the hydrogen atom itself is taken your best supercomputer hours to make a good model. Once you introduce that third third proton or particle into the
yeah,
nucleus, and
the
we get to
three-body problem.
lithium, it is everything breaks down with our computation. Yeah, it is just impossible to do with our current computational power. So like trying to model a cell on a high energy scale would be a thing that hopefully can happen, but probably will not happen for millennia.
Yeah. Yeah, there's a finite amount of information that we can simulate in the universe. Just this isn't on the questions, but as we're talking about it, do you believe in a finite or infinite universe?
I think it's infinite because, like, as far as I know, it is continually expanding. We have a finite view, so like the universe is always expanding. The universe is infinite, but because light has a finite speed, the amount of the universe that we can see is limited.
Okay.
So the amount of universe we can see is based off the life of the universe. So if the universe is 14 billion years old, we can only see the speed of light times 14 billion. Like, I don't know the exact distance that is, but that's how far out we can go. And if all honesty, and that's just because that's the time it takes for the light from those objects that were out there to hit us.
Okay. Yeah.
So that's how I view it.
Yeah. And then going more to terrestrial concerns, a question is about the topic of carbon footprints plus greenhouse gases. I was wondering if scientists think there's a way to minimize the fossil fuels that we are burning for energy.
So if you mean like if we can make fossil fuels clean, I would say from my understanding, like that's very hard to do just because of the carbon monoxide that is produced. You could make a system like with a car where instead of having your exhaust pipe pump out the gas somewhere, somehow like captures that gas so we don't release it into the atmosphere, and then we could try to use that gas and pump it into uh soils and stuff to trap it again. But that probably isn't a feasible idea over doing renewable energy sources. Um, just because like the cost and kind of the inefficiency there is probably just you're spinning the wheel a lot more than you have to. While if you went to with renewable energy sources, you don't have to worry about trying to capture this again and stuff. But it could be done. I would say, and I know some people have contentions, but I would say honestly, the best way to reduce, like, fight against carbon emissions to help climate change is honestly nuclear. For a few reasons. One, we can try to do like a worldwide nuclear disarmament thing, so there's less nuclear weapons. That would be a positive. But nuclear is the safest form of energy production in the world. Oil rigs cause pollutions and have problems building the solar panels and building all of the other renewable energy sources have caused problems to the landscape. But like nuclear energy, when it is done right, which it has been done most of the time, is actually very efficient, does not create any greenhouse gases on its own, and provides a lot of energy.
Yeah.
And they have come up with new ways to take the nuclear waste from a nuclear reactor and then put that into another smaller reactor that can squeeze a little bit more energy out of it. And after that second time in that second reactor, it becomes unradioactive because of the new elements it produces. It will no longer undergo nuclear decay. Um, and we can use that you can use that byproduct or just dispose of it kind of like normal trash, kind of you put it in a landfill. Um, things like that. So,
Oh yeah. Nice. I didn't know about the second nuclear reactors. I know that uh a lot of the problems with Chernobyl back in the day were just that it was a very outdated reactor even for the 80s. So I know that they've been making a lot
yeah, like
of
at Chernobyl.
strides.
Also at Chernobyl, like there's a lot of like incompetence and grandstanding from the people in charge of the reactor. They were trying to show the government that they were better than other reactors, like quota wise, like, oh, we're producing more energy, we're more efficient, like, and all of that. And because of that hubris is actually why the reactor failed. Um, Also an interesting, I remember reading up ago, like 5 years from ago, some places are looking into algae that can apparently take the radiation and use it as like an energy source,
Oh yeah.
like from like
Yeah,
nuclear waste.
I read an article about how there's way less radiation than we would naturally expect to be at the Chernobyl site now because certain plants have evolved to actually eat up the radiation and like make it inert.
Yeah, because like you have to remember the only difference between the radiation that a lot of that is being produced at from nuclear reactors is it's just higher energy than the radiation we're getting from the sun. The sun is a nuclear fusion reactor, and we're using that to live. We like the plants take in the light and undergo photosynthesis with that, and that is just a nuclear reactor more or less. It's just a fusion one instead of a fission one.
Yep. All right. Yeah. A bold stance, but I would also stand by it. So, uh, going into space, or I guess going back into out of space, do you believe in the theory of parallel universes?
I honestly do. I don't think it's the way we perceive it in terms of like movies or books or anything where it's like, oh, there's a parallel universe for every instance in time. Because the reason I believe in parallel universes is because of dark energy. And I remember hearing a talk where they said if you look at dark energy and how it is being played out, you could assume that the dark energy, which is pretty much helping the expansion of our universe, is energy we cannot account for. So if we take into all the energy we can see, our universe would not be expanding as fast as it does. So there's extra energy in there somewhere. And someone explained to me, you can think of it like a balloon. Is before you put kind of blow up the balloon, everything's close. As you put more uh, energy into the balloon, you blow it up, everything expands outward. And this person was kind of talking about how if you take our universe and kind of assume that there are other universes around us interacting with us, kind of like on like, like we're in a bubble and we have these other bubbles around us and they're influencing us, we're influencing them. So they're putting energy into us, we're putting energy into them, and that's causing that expansion within our universe. So like I don't think it's necessarily like, oh, I chose to have you know, I chose to get a bagel instead of a muffin. Like there isn't like I don't think it's like two universes where one universe I chose a muffin, one universe I chose a bagel. I think
Okay.
it's there are mul other universes, but it's not like different timelines, if that makes sense.
Okay. Since we're talking about dark energy, you've explained a little bit of what it is. Can you uh also explain dark matter based on your understanding and whether or not the two are related because they both have the word dark in them.
Yes. So the reason they both have the word dark in them is literally just because we cannot see them. We
Yeah.
don't know where they're coming from. Other than that, they're not really related, at least like on a like any kind of scale. Like dark matter does not create dark energy, and dark energy does not create dark matter, from my understanding. What dark energy is, like I said, it's that extra energy coming from a source we don't know, increasing kind of the overall energy in our universe in the way it is expanding outwards, based off of the energy we can see. Then we have, and dark energy is always increasing. That is one thing. Um, but in terms of dark matter is matter we cannot see. And the way we figured out dark matter exists, or at least something's out there doing it, is when you look at like galaxies from far away. If you have like a heads-on spiral galaxy, so you can see it spinning, based off of taking observations, you can still calculate the minute amount of spin that it goes through from day to day because these things are massive, so they're spinning very slowly. Um, but you can notice they're spinning faster than they should be. And the only way they can, and what we mean by that is we can look at all the light and kind of in the galaxy, and that can tell us the spin rate because of the angular momentum. So we have the speed, we have the mass, we can figure out what the angular momentum should be from that. But where we realized we were getting slower, we were seeing higher spin rates than we should based off of the amount of mass we were seeing. So that tells us that there definitely has to be this extra matter in there that we can't see, or dark matter. You can also see it by from other galaxies. If you look a little less heads on and more at a side view, you can see that the galaxies have stronger gravitational pulls with some distant objects than they should, and that is called a halo. And that halo comes from it's larger than it should because of the dark matter within the galaxy as well. So like we don't think like there's dark matter like in us from our understanding. Like we don't have like this matter we can't see. We think dark matter is some type of like cosmic thing. Like it's part of like gravity or not gravity, but like part of matter that we just can't see, but we don't think like we or the Earth is made of dark matter. It's just like somewhere between that we can't perceive at the moment.
Okay. Yeah. So, uh, talking a little bit more about astronomy, I have a question. What happened to the stars and constellations we used to be able to see out clearly here in the Inland Empire? The sky used to be full of stars, but now we only see a few. Is it because of light pollution or did they actually die off?
So honestly, it's very hard. I would say it's probably not them dying off. Stars have incredibly long lifetimes. Our own sun has at a minimum a 10 billion year life cycle. Um, and a lot of other stars have just about the same. Even the largest stars, which burn bright and die quickly, still live a good billion years. So we're probably not seeing them die off just because of the number of stars we see. Now, there's are certainly stars dying off, one way or the other. I just don't think they're just really far away and we wouldn't see them with our naked eye. So depending on where in the Inland Empire you're talking about, so if you're talking about like a place like Joshua Tree, the reason you might see less stars is potentially the pollution, because the pollution affects the light coming in and out, and could cause more reflection of the light, so dimmer stars aren't able to make it through the atmosphere any further. Now, if you're talking about being close to populated areas like LA, Riverside, San Diego, just like any city, it might not be a thing you think about just because you might have lived there for a while, but cities have probably expanded. And as they expanded, that light, even if it is suburbs, that light is enough to kind of block out some of those fainter stars in the night sky. So that light pollution could also be causing a loss of those stars.
Okay. Yeah. So, uh, talking a little bit about Earth itself, how does Earth's magnetic fields change over time?
So with Earth's magnetic field, it has switched a few times. So I know looking at some ferromagnetic rocks down at the surface of the ocean, when they were coming out of the Earth as magma, before they cooled, they were affected by the Earth's magnetic field, and they had all of their dipoles and everything align with Earth's magnetic field at the time. So we can see if we take a chunk, we can see this alignment change with time. Now we don't know exactly what is necessarily the process of changing this magnetic field, like why it switches, and we don't know the time scale of the switch. Um, so we don't know if we have, a few years before it switches again, or hundreds of years before it switches again, but it does switch. And we can see that by looking at these like this lava that has like magnetic material in it. And before it cooled down to where it couldn't move anymore, they all aligned with the poles. And we've seen like the orientation of these magnetic fields switch back and
Yeah.
forth.
And then with the time scales, or like you said, we don't really know how long it takes to switch, but we do know, I think, that the magnetic field has been weakening in recent years. If I
Yeah, we have
remember
been
correctly, that
noticing
is something
magnetic
that's
fields.
happening.
Yeah, we have noticed the Earth's magnetic field is getting slightly weaker. It's not like, half of what it was 10 years ago or anything, but it has been getting slightly weaker with time. The biggest fear with the magnetic field stuff, we don't think it will really happen because we still are here, like alive, is when the magnetic field switches, if it does it very quickly, could destroy a lot of electrical components because of the induced current that would be generated by the magnetic field completely doing a 180. Also, if the magnetic field goes very slowly, we like it goes from like a high number to zero to a negative number, if we're at that zero mark for or a very small magnetic field for a while, then we don't have anything protecting us from a lot of the ionizing radiation from the sun, like UV, X-rays, and ultraviolet, or not ultraviolet, gamma rays. And that could be damaging to us, like biological stuff on Earth. But based off of the fact that, it has flipped multiple times already, and there are still living things on Earth, that probably isn't the case. It's probably not going to be disastrous. But if
Yeah,
it does flip, the worst would be just a lot of electrical components getting damaged.
yeah. Okay. Uh, uh, Also with magnetic fields, can magnets be made out of non-magnetic objects? And I think there's a bit of this is going to be a twofold question about what type of objects can be magnets and what type of objects. How do you make an object that doesn't initially have a magnetic field but can be a magnet into a magnet?
So I think most things cannot become a magnet. So like wood, um, couldn't be a magnet. Plastic couldn't be a magnet. Now you could give the wood and the plastic a charge, such as like static electricity, and that would attract things with the opposite charge, but that's not necessarily magnetism. But what you can do with some materials, so like you can make iron, steel, nickel, if I'm not mistaken, those things are not necessarily magnetic off of like right off the bat, but you can make them magnetic. And the way you can make them magnetic is in put an electrical charge through them, which is an electromagnet. And the reason you need an electrical charge is, if you haven't covered this already, is electricity and magnetism or electromagnetics are they're intertwined. So if you have an electric field, you create a magnetic field, and all of that. So when you use this electric field within this metal, it creates a magnetic field outwards that can act like a normal like magnet you would get like for like a bar magnet. So you can make certain metals magnetic, but you cannot make everything magnetic. And you can, if you kind of wrap that piece of metal that isn't magnetic already into some wires and have a high enough current go through it, you can create electromagnetic material.
Yeah. And then something that this is actually a condensed matter problem. So if you want to take condensed matter classes later in undergrad and you are wondering about magnetic fields, then I would take condensed matter because it does explain very specifically what materials are and aren't allowed to be magnets. And basically, it ends up being metals with an odd number, with a number of unpaired electrons, which means that uh, the electrons have this property called spin, which can be is a property of or is a in units of angular momentum. So it can be thought of as how an electron spins clockwise or counterclockwise around a nucleus. And what ends up happening is that if all of the electrons, uh, first you fill up according to the Pauli exclusion principle, which is something that you're going to see in chemistry, first you're going to fill up all of the electrons spinning in one direction, and then you're going to fill up all of the electrons spinning in the other direction. So if you don't have, so basically what happens when you have them spinning in the other direction, as well as, or one electron spinning in clockwise and one electron spinning counterclockwise, is that their angular momentum or their spin cancels out. So they're not able to carry a magnetic field because it turns out that because a magnetic field, thinking about it in a classical way rather than a uh, quantum mechanics way, the magnetic field is caused by a moving electron or a moving charge. So if you have a total angular momentum that isn't zero, then that means that overall the electrons are going to be moving either counterclockwise or clockwise. And that means that it can be magnetized because overall you are going to have this spin, which can be, when you apply a magnetic field to it, can cause the magnetic field can cause the spin to align in a certain way. So
Mhm.
that's basically what happens with uh, magnets, or that's what allows magnets to be, or yeah, that's what allows magnets to be magnetized, and what allows, say, iron to be a magnetic material, or possibly magnetic material, whereas like wood, which is more complicated and is pretty electronically inert, isn't going to be able to be a magnetic material.
Mhm.
So I kind of just stole your question, but
I was like, you seem to understand it better than me because I did not take any solid state physics classes except the one I had to do in undergrad. And all I remember in that one was learning about uh, the crystal lattice structure and the inverse of the crystal lattice structure, which it seems like everyone uses the inverse of the crystal lattice structure to understand what phonons are.
yeah. So the inverse of the crystal lattice structure gives us momentum,
Yep, the momentum
is in
state.
units of momentum. So that ends up being very useful for uh so this isn't covered in the class and it's not going to be in any of the lectures so far, but if you have a lattice structure, uh then there is also a mathematical where a lattice structure is a bunch of actual particles placed in a lattice, which means that they're placed some distance apart like a crystal. Then there is going to be a mathematical concept called a reciprocal lattice, which is uh, when you basically instead of finding the actual position of each of the electrons in the lattice, it finds kind of their momentum in a or their crystal momentum in a very kind of esoteric kind of way, honestly. But what is interesting about that is that because it finds the momentum and because light has momentum, when you bounce light off of a crystal lattice, what shows up when you read the light? So if you pass light off of like a CD, I don't think they even have CDs anymore, but you pass light off of crystal or like a CD that has a lattice structure, then what you're going to see as the laser beam bounces off the CD or the crystal is going to be the reciprocal lattice structure instead of the actual material or the actual structure of what you see. Because the light has momentum, that momentum is going to transfer the information about the reciprocal of the lattice, which means that by bouncing off light, we can see the actual reciprocal lattice, and then from there we can recover the actual position of all of the electrons in the real lattice that we're looking at. So this is one of the more fundamental things for material science and solid state physics. But oh, I have a fly on my breakfast right now, so I guess I don't get to eat that. But uh, this is what one of the more interesting tools that we use for solid state physics and one of the more basic tools. And I don't think that the person that we're going to be getting in that does condensed matter actually does that much light work or work with lights or lasers or anything like that. So I think it is a good chance to bring this up
Hmm.
before interviewing them. And then, uh, bu- 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 you mentioned, so we've mentioned that magnets are based off of electricity and moving particles, but what about static electricity? And why does it
Static.
sometimes shock us?
Yeah, so static electricity is just the buildup of charge. So kind of like an analogy I can kind of give is say, and like why it shocks you is say, you go from being, like an average person, you probably can't just buy a brand new car super easily, right? It requires a lot of input. But if you are instantly become a billionaire, buying a new car is pretty easy. You can easily transfer that money to the ownership to get the car. So it's that build up of stuff. So in this case, instead of money now, it is charge. As you build up more negative charge, as you kind of shuffle your feet on a carpet, rub a fur kind of pelt on something, it builds up a negative charge. And to everything else, if you become very negative, everything else looks very positive to you now. Even though the other stuff hasn't changed its charge, something that is neutrally charged is going to look very positive compared to you or the object that is now very negatively charged. And thus, because these negative charges don't kind of want to be next to each other, they like the negative charges do want to repel each other. They will jump to the more positive seeming locations, and that can, if it's a sufficient enough charge, create like that spark, or that shock that we feel.
Okay. Last question that I have from the students before I get into a couple of just general questions to close this out is, do you believe in life beyond Earth and how would you communicate them? One of the ways that I think is really interesting is the golden record that we placed on the Voyager.
Voyager 1 and 2. Yep.
Yeah, or on the Voyager spacecraft, which is meant to communicate where the spacecraft came from to people who didn't speak English or any other languages that we could understand. So
So I know, oh, go ahead.
go, or no, so I was just going to pass it off to you.
Yeah, so the golden record I know is really cool is it is an actual record made of gold, and it's made of gold because gold does not tarnish. So we didn't want the record to degrade for as long as possible. So unlike other metals, gold does not tarnish easily. And also it has, as far as I know, every language saying like hello, saying a phrase, kind of like introducing themselves in different languages on Earth. And on the record, on like the casing of the record, it has very like not in English, but trying to use mathematical ideas and principles, how to play the record, how to kind of download or reconstruct the images put on the golden record. It has kind of using large stars within our galaxy, like very noticeable stars in our galaxy, where we would be in relation to those stars, and a bunch of stuff like that. Um, and honestly, like for me, since I think the universe is infinite, we exist based off of probabilities. And even if that probability is small, if you multiply a small thing by infinity, you will eventually get above one. So I would say there is life outside of the universe, outside of Earth. Now it could look different. So we call ourselves carbon-based life forms because if you look at the periodic table, carbon has four valence electrons, meaning it can take in four more valence electrons. The way I like to think about it is every empty valence electron is an atom you can connect, kind of like Legos and stuff like that. So carbon is the basis of our life on Earth because it can make four connections, so it can make these large structures that create cells, that create organisms. But if you look in the same column as carbon, you have stuff like silicon, which is much more rare in the universe. But we know there's pretty much entire seas of the stuff. I forget on what moon,
Mm.
but on one of the moons of Jupiter or Saturn. But like it's pretty much all made of liquid silicon. So there could be silicate-based life forms just because it's that same property of having four connections, so you're more likely to make molecules. Now, it could be completely different in the way it looks and the way it acts, just because of the way of how it's made. But I do think there is life in the universe, and it would probably be based off of any of the other elements within that column with carbon. We'd probably more likely run into a carbon-based or silicate-based life form, just because compared to the other two in carbon's column, it is very, very minuscule amounts in the universe compared to the other two. So I would say just based off of numbers, it would probably be carbon, and then silicate would be second.
Okay, nice. And then I also want to point out that the record does actually work as a record, and I think it has
Yeah.
Johnny B. Good on it.
Yeah, like so like they try to like encapsulate humanity a little
Yeah.
bit. So like there's images on there. There is like recordings of people saying hello, like I said, there's like songs and stuff. Like it is not just meant to be like here we are. It is also supposed to be like this is who we are as a species, and this is where we are. Though I will say, since the invention of the radio about 100 years ago, we'll say 110, uh, since light takes, every year the radio signal is traveling is 1 light year. Light takes, though, the time to get there and get back. We know at least there is no life that has been able to pick up our signal and decided to return a signal within the last 55 years. because it takes 55 years. If we've been producing these radio waves for 100 years, it's taken 55 years for them to get back and 55 years to then reach Earth again. So within the last 150 years or 110 years, we know there is no life that is 55 light years away from us that has at least been able to pick up our information and wanted to talk back to us.
Yeah. Yeah. And then yeah, the so I don't think 55 light years is huge on an astronomical scale, but it is still a big enough conundrum that it hasn't occurred that there is a scientific principle or like maybe just like an intellectual principle called the Fermi paradox, where it's different reasons for why we might not have heard back from them. And then I think honestly, a lot of
Yeah.
them are really silly and kind of assuming that aliens are just out to get everyone. But it is something that I just wanted to bring up just in case somebody wants to look up more about the Fermi paradox and about that the reasons that we think we might not have heard back in that 55 light year bubble. Okay, and then uh what are some of the most exciting unsolved questions in physics right now?
For me, I would say just the beginning of the universe. Like, how did all of this start? And kind of unifying gravity with the rest of the fields. So, what I mean by that is we know the electromagnetic field, the weak nuclear force, and the strong nuclear force are connected. They're all connected. But gravity is the fourth force, and it is not connected to the other three. So we're trying to find particles or some way that connects gravity with the other three. So, but that kind of unsolved mystery, if that was discovered, would be really big. And then same with kind of, the actual beginning of the universe. We know the Big Bang happened based off of a bunch of information uh, gathered after, and we're able to see all the way back to like right before the Big Bang happened. But because all of the light that we can currently detect is too dim, which is the cosmic microwave background, which is everywhere, which is the at the earliest picture of the universe. Because we can't peer through that just because of the nature of the early universe. We don't really know what happened exactly, but people are trying to do studies and trying to collect data that could help us peer through that cosmic microwave background a little bit better and see, what was the initial conditions of the Big Bang.
Yeah. Okay. And then the final question, you can
So kind of
bring
be
up
my
anything
answer.
that you wanted, or you can bring up anything else that you want to talk about after this if you want to. But the final question that I have is you're currently working as a science teacher. So, what do you find is the best way to inspire students towards science?
I would say honestly, giving them the ability to investigate their own inquiries as best as you can. I know last summer I was at a workshop where I learned about like mastery-based learning, which is you don't just stand there and lecture and kind of talk at students or give them problems to do. You give them a criteria to meet, an objective to meet, and you give them time to work towards that objective and to kind of answer questions at their own pace a little bit in their own way. So I that kind of like letting them have inquiry, have questions, have giving them the tools and the ability to answer those questions, I think is honestly the best way and the most fulfilling way to kind of teach students science because I'm not there to like lecture at them. I am there to help guide them through the process.
Okay.
And like that moment where they like get something through this process, they aren't just, oh, I have the answer now for the test. It is, oh, I understand this. I have mastered it, which is why it is called mastery-based learning. And like they will remember this experience more than just reading it in a text or looking at it on in a video or seeing me write it up on the whiteboard.
Okay. Yeah. So I start out with the generic
Yeah.
first job interview question to like tell me about yourself. So I'm going to end up with the generic last job interview question, even though you're not interviewing for a job, which is, are there any questions that I should have asked that I didn't?
Let me think. In terms of my profession or in terms of like the interview questions? Like, like are you asking in terms of like
Or
anything you should have
just
asked
like
the
anything you
teacher
want to
or just
share.
in Hmm. uh not much. Like we covered a lot of the topics that I had like I've kind of had some of these questions before and we've covered a lot of them. I would say honestly the only thing that I would like to share or say to include is like even if physics isn't what you are into, like is not the field of study, I would still take the ideas of inquiry and the ideas of like seeing why things work the way they do in any field. That can go to biology, that can go to math, that can go to finance, that can go to politics or whatever you're interested in. But just kind of understand, don't just take things at the face value, understand why those things happen, why those things occur, and kind of take the skills hopefully you learned in your science and physics classes to apply them in those areas.
All right, great. Well, I would like to thank you for giving us your time today. Uh, and with that, I would just like to, or with that, we can just finish up. You don't have anything else to say, so I would like to thank you again. This is Mr. William Baker from Maryland, or I think you gave the East Coast, so I might have just doxed you a little bit, but uh, yeah, from the
Yeah,
East
I said I was
Coast
American.
science
I said I was
teacher and a
American.
very, very good interview subject. All right, thanks.
Thank you. Thank you for allowing me this opportunity.
All right.